Welcome to my presentation. I'm Marc Vuffray from Los Alamos National Laboratory, and I'm happy to talk about this joint work done with colleagues at Los Alamos, Carlton, Andre, and John. So this presentation is about what we can learn by performing experiments on a single qubit. So we started to look at the D wave that we have here in Los Alamos. You can see on the left the representation of the chip here that we have in Los Alamos. And we started to look at this machine mostly to model what's the relationship between the input and the output of the D-Wave machine. This way, we're also hoping to design diagnostic tools to see if the D-Wave behaves in the way we expect it does. So we started to look at small system of a few cells. And these systems already exhibit such a rich and complex behavior, and we thought maybe we should go for a simpler system and try to understand them. And what is more simple than just using a single qubit? So this is what we'll do in this talk, just look at what we can learn from a single qubit experiment. And the system is so simple that there isn't much you can tweak. You can essentially change the input field. So this is the prototype of the experiment that we'll do. We have an input field that is positive or negative, and it favors either the readout being plus or minus. And we change the value of this input parameter, let the system anneal, read the value of the spin, which is either plus or minus 1, and we repeat this experiment 5 million times for a particular value of H in. This way, we can have an accurate description of the probability of the spin being plus or minus with respect to the value of H in. So if you look at the typical values that you will retrieve from a single spin, this is what you have. So you play with the wide range of H input, ranging from minus to plus values, and you collect these samples and represent the probability of observing the spin in a state plus. So you see that here, if the field is positive, the spin will be positive as well. If the field is negative, the probability of observing a spin being positive is 0, which means the spin is mostly negative. And you see that if there is no field, the field is close to 0, then you have equal probability of finding the spin in a state plus or minus. So how can we model this type of response? So we can think about classical statistical mechanics and try to model this response using what is called a Gibbs distribution. So how does it work? This is what is called a classical Gibbs distribution. You postulate that the probability of seeing the spin in a value plus or minus is proportional to an exponential of the field, the value that is input, times the spin. And in front you have this coefficient that is a proportionality factor, which is called the inverse temperature. Classical thing to do, and this is what is predicted by classical statistical mechanics, if you want to look at the behavior of a spin that is subject to a magnetic field. So let's look at this prediction here and do a fit. So if we have a temperature of 10.4, this is what we find if we fit, you see that this prediction from StatMech fits reasonably well or very well the curve that we have measured experimentally. We can stop here, right, and be happy with the result that we have. But the question is how accurate this model is. Like, maybe it looks very good, but is there some discrepancy that we missed when we did this plot using this representation? And to see if we're missing like some finer behavior here with this model, we have to change scale. So let's do that. Let's change scale. Instead of representing probability, like it's here on the right, this is the plot that we had before, we'll try to represent kind of a relationship between fields, trying to play with the same quantities, like field to field. So here is the classical Gibbs distribution, written on the left, where you have this, this probability proportional to an exponential and the field times the spin. Now, we can say the same with the measured probability. let's say the measure probability should also behave like a spin times a field. And let's say the temperature is 1 in this case. So this is what we would expect when we to reconstruct when we measure the probability, and the orange is our model of how the probability behaves. So using those two different representation of probabilities, we can draw a relationship between the field themselves. It's like the field we measure versus the relationship of the probability with respect to the input field. So here it's very easy to see that you just have to equal the two fields in the exponential to find that, you know, statistical mechanics will predict a linear relationship between those two fields. So what does it imply in our graphical representation here? Is that mostly, if you write a probability like an exponential of some real number, the values close to the origin will be linear, and here it kind of emphasizes this part that is very close to 1 in an exponential scale. And this is what happened. So it's exactly the same plot as before, the same orange curve, but this time it is displayed in this H-in, H-out plot, where you have this linear relationship between the field that is input and the one that is reconstructed from the measured probability. It's just linear in this case. The temperature that we found, our inverse temperature, is 10.4. Now let's draw the measured points. And this is what we get. So you see that it fits very well when you have very small values of H-in. But when H-in is large in magnitude, either positive or negative, it starts to deviate and flattens. And this was very hard to see before because those values of H-in corresponds to probability that are very close to 1, but using this new scale, we can actually emphasize that there is a difference between the linear scaling predicted by classical StatMech and the one that we measure. There is some discrepancies. It is actually small in probabilities, but it's significant as you see the orange classical plot like doesn't go through the error bars that we have. So there is clearly a deviation. So how can we explain or model this deviation? One way to model this deviation, and this you will see that it explains very well what's going on, is to resort to quantum StatMech. After all, those qubits are in a very cold environment, so you expect them to behave or to exhibit some quantum behaviors. So this is what what quantum mechanics predicts, statistical mechanics, when you have a system of one spin in an equilibrium, but with two different fields, like one which is this H-in, and another one which is a transverse field applied on the qubits. And this is what this, for those who are familiar with the density matrix formalism, you have this density matrix that is proportional to an exponential. You see that it resembles very much to the classical one, where you have a temperature, H independence, and the transverse field on the z-axis. But now we have something new, which is a transverse field on the x-axis proportional to H-in. And this variable xi, this new variable xi, is the proportionality factor of the transverse field. So from that, we can also reconstruct a quantum field input-output relationship. It's a bit more complicated, but you have an explicit formula that tells you the field H-out is proportional to some formula that involves the density matrix and the quantity H-in. Now, if we draw this, this curve, you see that for a very similar temperature, it was 10.4 in the classical case, it's 10.5 now. You see that the curve matches and repredict this plateau at the end for a certain given value of transverse field gain. So this is why it saturates, because you have a transverse field in the model, and it seems to explain very well and very much what we see on the plot. So seems very successful. But is there still parts that we're missing here in this quantum story? To see even finer discrepancies, we'll have to zoom in on the plot. And since it's roughly symmetrical. We'll just see what happened on the positive portion of the plot. So let's zoom in. So same plot as before. I've just emphasized a bit more this positive portion, and you see that it fits very well in this plateau, that it goes through the error bar, very well near the origin, but there is something that is not perfect here. And of course, the plot, as I mentioned before, it's an exponential scaling for these high values of h out, and you see that the error bar are pretty large, so it's totally okay to not be perfectly inside the points. We're still within the error bars, but here the error bars are much smaller because we have a lower value of h out, like order of magnitudes lower in the probability space. And then if we don't really go inside these error bars, and it's a much consequent miss than the one here in the plateau. So here we have a mismatch that is significant. It is small, but it is significant. So that's the new challenge, is like, okay, we have these quantum models, it predicts the plateau, so it's already better than the classical one, but is there a way we can say something about this mismatch? And yes, there is a way. And the way here is to consider noise in the fields. So we'll still consider a quantum model, but this time we'll say, instead of having this quantum piece density matrix, we'll add some new variable. And this new variable will represent noise in the field applied on the regular z-axis. And this is what we'll get. So we have new variables. This density matrix is proportional to the old quantum model, right? You have the exponential and the old quantum model, but now we have a new regular field on the z-axis, and this field is noisy. So eta is the standard deviation of the noise, and S is just a noise realization, which we will take as a random field. So you have to see that the input, you input H in the system, randomly the system will add another field with a random sign and magnitude eta. So you get a mixture of quantum model. You can also like derive a new field input output, and here you have to take the expectation of all the possible noisy realization, which are just 2 plus or minus 1. At random, 1/2. So you'll get something new. If you do the plot, this is what you see. You see that for a non-zero value of the noise standard deviation, so it is significant here, the model actually starts like the quantum one, but deviates here to go through the measurements and also end up with a similar plateau in the end. So this one can actually explain or predict the behavior, this discrepancy here that we see on the measurements. Okay, so what are the difference qualitatively between these two models? The big difference is that we see that they predict different effective temperatures. And this is the most important part. Of course, the noisy model takes into account the noise, so we also reconstruct some standard deviation of noise. But most importantly, we see that they predict or they reconstruct different effective temperatures. And why is that? It is because if you plot those two lines that represent just linear plots in temperature, you see that the red model mostly fits the lines or the behavior at the origin, while the noisy model fits what's going on after the origin. So here. And this can be explained by looking at the effect of the noise in the model. In fact, when the input field is small, mostly what dominates the behavior of the machine is the noise. So you'll get like it's not really the temperature, it will be reduced by the effect of noise. When the input field is large, then the noise is small with respect to the input field, and you mostly get the real, or let's say, more effective temperature of the system. So the quantum model cannot give you an effective temperature that is valid, or a response that is valid, but only in this noise-dominated regime, while the noise-aware model actually understand this part is dominated by noise and give you the temperature which corresponds to this regime that is not dominated by noise-free. And this is what you get. Now we can repeat this experiment on the entire chip to actually assess the value of the noise for each qubit. And here you have like represented the full histogram that we have learned from our D-Wave chip. You have this noise distribution, different field noise distributions. These are the standard deviation time temperature for each qubit. And you see that most of the qubit have noise that is ranging between these two values here, between 0.3 and 0.5. And there are also a few qubits that are completely noiseless. And you can do that for the whole chip and map the different qubits with respect to the noise values. I will not show it here, but you can see, you can repeat this experiment through time and see that it's actually very stable over time. So you can use this experiment and this model to actually probe and learn what is the noise in the machine. So if I have to summarize these results, this is what you get from the single spin experiment. The single spin experiment displays three kind of behaviors. For low values of the input field, there is like a classical regime that is mostly dominated by noise, which will at some point will not fit the experiments because you have this part, the second part, for value of H3 that are moderately high, where the system is mostly noise-free, like the input field is much bigger than the noise. And this can be captured by a classical noise-aware model that kind of change its slope over time. And if you want to capture the plateau that happens for a very high value of Hin, you need to resort to a quantum system or quantum statistical mechanic description of the system that is also noise-aware. And this can represent the full range of the behavior of the system for all values of Hin. So in conclusion, I would say that understanding, capturing quantum and noisy behavior is essential if you want to model the D-Wave response, even if you take a single component, one qubit. And the noise model is input here in a way where you have a superposition of different models. So it's called a mixture. You have different models for different value of the noise. And this cannot be easily captured by one single Gibbs distribution. So you have very different behavior and you have very different effects that are displayed if noise enters into the game, because noise mixture are different from a single Gibbs distribution. And the last thing is, as you saw, you can use the single spin experiment to probe and map the field noise in the machine. And that can be useful if you want to fine-tune particular experiments or mitigate the effect of the noise. So these results will be soon be appearing online in the title Programmable Quantum Annealers as Noisy Boltzmann Samplers as part of a bigger studies of noise and small systems in the D-Wave machine. Thank you.